Hi, everyone. Good morning. Hope everybody's doing well and enjoying the sunshine on the days that we get it. A lot of you are going to have questions about grading. I will be sending out a video explaining that all when I get some further instructions, either tomorrow, later that day, or the next day. Again, everything's really fluid. Right now, all I can say is we're going to move status quo. I'm going to scale back some things, but just remember, I'm looking for effort and participation versus really like difficulty. But here we go. We're going to start out with cosmology, not cosmetology. That's a little hairdresser joke, if you will. But here you go. Does anybody recognize this picture right here? This is actually the painting. This is actually a painting from a long time ago. You actually know this person. He was in the Cosmos video. Remember, he was asleep, had a dream, expansive universe. Yes, his name was Giordano Bruno, if you remember that. Okay, and basically what Giordano Bruno was, he really wasn't a scientist. He was more of kind of almost like a philosopher in a way. He just made an educated guess, but the idea was that he said that the universe was boundless. Well, we're going to talk about that a little bit. Well, the expanding universe, okay? So here is this ratio of the expanding universe, okay? And here is this idea of recessional velocity, and that's basically just kind of like uh, centripetal velocity in a way, the idea of rotational velocity, okay? Speed of light, wavelength of light, and so forth and so on, okay? Now, what does this all mean? Well, what it means is what technically IB wants you to know is recessional velocity of a distant galaxy is directly proportional to its distance. Well, what the frick does that mean? Well, what does that mean? In other words, the further away a galaxy is, the faster it moves away from us. That's why when we talk about the parallax method and everything like that, we said that things closer to us seem to fly by quicker. But if you think about it like an arc on a circle, if you have an arc on a circle, and let's just say it's flying out here, for it to move across our sky, it's kind of like the inverse of that parallax idea that things closer seem to be moving faster. Well, if it's farther out on that, shall we say, arc or the string from where we're at, we have to assume that it's moving much faster. Its centripetal velocity is much faster. And that goes back to circular motion when we were spinning the bulbs on the string. We know, like on the merry-go-round, we said if you were on the edge of it, okay, you feel like you're going to fly off of there versus standing in the middle. It's the same idea, just that we're talking about planets instead of like a bulb on the end of a string. So basically what we're saying here is that velocity is proportional to its distance away. And we can substitute or insert, shall I say, Hubble's constant into there. And remember, we've dealt with that a bunch before. Okay? The expanding universe, this idea that we can see as things are farther away, as they expand farther away, it's going to get faster and faster and faster. Okay, you should have learned about redshift and blue shift in physical science. Redshift, okay, redshift would be as objects are moving away from us, and blue shifts are moving towards us. And the reason we know that is because redshift have a longer wavelength. So that means if you think about a slinky or a spring in your hand and you move that slinky away, you notice that the wavelengths increase and the frequency decreases. That's red shifting. That's the red line. It has a larger wavelength, lower frequency. Versus blue shift, that spring or slinky would be moving towards you to make the frequency higher and the wavelength smaller. And again, we know that blue and violet have a higher wavelength, or excuse me, a lower wavelength, higher frequency. Okay, now I leave this on here because some of you are super smart at math and you like to look at this stuff. I mean, deep down, you don't like to admit it to your friends, but you do like to look at these and try to figure that out. And what this is basically a ratio, okay? It's the R TOBS is the scale factor of time, okay, versus what we see of light now. So basically it's that idea we said if we look at the light from a sun that is leaving a billion light years away and it takes a billion years to reach here, how does that light change over that time? I'm never going to ask you to like solve this per se, But just the idea that when you see that, we're talking about a ratio, just the simplest things about the ratio of lights of what was emitted versus what we see, the wavelength that would actually have been emitted from the wavelength we see. So a lot of times we have these two and this one, and we're looking for what is the actual wavelength. So maybe a star appears to be green to us. Well, it may have actually been red, but by the time it gets to us, the wavelength has changed, or vice versa. If z equals 3, then the scale factor of time that light was emitted is r to 1/4. So the galaxy expanded by a factor of 4 in the time since light left that galaxy. So just like I said, you're gonna use that equation right here. Right here, you're going to use well, I'm sorry, you're actually going to use this one right here, and you're going to substitute in for z. You're going to substitute in for your R term, and you're going to get your answer right there. And if you want the answer to that one, it is in your book. I left it there so that you could see it all broken out a lot better. So it's in your book, and let me just real quick look. I know what page it's on. I had it open. Pause for dramatic effect. Oh my goodness. Oh my goodness. Yes, it's on page 438. And again, that is solved out in your online solution manual. Okay. All right. So it's all worked out in there for you. Again, not going to ask you anything on a test or quiz about that, other than just understanding the breakdown. Okay, the Big Bang model. You guys should all know this, that basically the universe started from a tiny exponentially small point and exploded out of there. This basically just shows you how he calculated using the Hubble Space Constant the age of the universe. Kind of cool. Okay, this is important. There are 6 points on pages 439 to 440 in your book. These are basically, they might ask you a question, or I might ask you a question on a little knowledge check here about I might just ask you of these three proofs of what we think happened with the Big Bang, which ones are right? Okay, something of that nature. Cosmic background radiation is the biggest proof that the Big Bang existed. This idea that there's radiation emanating outward from the center of our galaxy and it continues to expand outward. Okay, so this is like the number one proof that all science agrees on. Okay, here's a really short 4-minute video. It's pretty cool. It's kind of an overview. It's out of another video, but it's really neat. So why don't you watch that and come on back. All right, well, hopefully you watched that, and it's really cool little video. Just kind of gives you like an overview of all the principles that we've talked about, kind of all the chief characters in the story, if you will. Okay, so this is no longer in your book, but I really like to talk about it because this is kind of like the really interesting part. Like there are some models of the universe. There are 3 proposed outcomes for the development of the universe. There's the open universe, which is kind of like a real positive view of the the universe, where it just says it's going to grow, it's going to keep growing, and it's just going to keep growing forever and ever and ever, and all will be good in the world. There's a closed universe, which is kind of the opposite, which means we're going to hit some kind of functional limit, and then everything's going to kind of come back and collapse in on itself. Sometimes we refer to this as an oscillating model, kind of just like an oscillation of a bulb, or some people like to think of an accordion where you stretch it out as far as you can, and then when it stretches to a point, it can't stretch anymore, so it has to come back in. Okay, and then there's the flat universe, and this is somewhere in between these two. Okay, where basically the idea is it's going to expand to a point, but then it's going to hit some kind of point, and then we're going to be good, and it's just going to stay there. So that's kind of an interesting one. The outcome depends upon the mass density, or the amount of matter per unit volume available to provide gravitational attraction. Okay, that's an interesting thing. But basically, it's saying the idea that the mass has to be somewhat close enough that it's holding the other masses together. um, but not far enough to where it can't. So, for example, here's just some animated ways of looking at it. Like this one right here. Anybody want to take a guess which one this would have been? Real quick, go back. So we have open, closed, and flat. This one would be, yeah, this one would be an open. Okay, this would be an open. All right. This one, where it comes and it's crashing back into each other, we'd like to call that a closed, right? That would be a closed. And then this one is actually, it really wouldn't be a flat as much as it would be what they call the big rip or the big rest in peace, basically where things get so far out that they just rip apart. Okay, so it's not really the flat, but it's kind of this idea that it would get so far out there that it would just kind of fizzle out because eventually we'd be at this limit. So we have this chart, okay? If there is a constant rate of expansion, excuse me, there's a constant rate of expansion, it'd be just growing and growing and growing. That's the black line. The open, if you notice, continues to get open. And yeah, it's going to take, I mean, theoretically, it would flatten out over time, but it's pretty much keeps it going up forever and ever and ever. As you notice, a flat here kind of comes and flattens out. Okay, and then the close is just this. Now, most people would think that later on down the line, this thing would do another hump and do another hump, and uh, and that's what we talked about in class. Like maybe if we were part of a closed universe, we've already had this conversation. Maybe all this has already happened before, and we're just repeating it. We're kind of stuck in this loop. Okay, kind of crazy to think about. And then basically this idea of critical mass or critical density versus uh, mass density. Okay, so the idea of how would these be related? Well, where would these two be equal? That one should be pretty easy to figure out. Which one would be equal? Would it be open, flat, or closed? Where P would equal P naught. Well, that would be the flat one. Yeah, that would be flats right there in the middle. They'd be equal to each other. Okay, so let me ask it this way. Oh, right here, theoretical density that would create a flat universe. Perfect. Okay, so I have a question for you. In which of these we're left with open or closed, would the critical density, that means the density of all the mass would be greater than the mass density. Okay, that didn't make much sense. Let me say it again. Where is there going to be more mass? Where's there going to be more mass than the density that it needs? Let's just say it that way. Like, where's there going to be more mass than the density? And that would be the open one. That would be the open one because what it's saying is there's more mass than the critical density. So that means that it's just going to keep going forever and ever and ever. Okay? Versus when there's more density than there is mass. Okay, when there's more density than mass, that means that we've got a lot more density. It gets very, very dense, and there's not as much mass, so it can't control that mass, can't counteract it. So then it's going to come crushing back in because it's so dense. Okay? Again, just want you to kind of see those models right there. I know that last part's a little confusing, and I'm not going to really test you on that either. Okay? Really, we have two more little videos here. This one's 5 minutes. What will kind of explains the big rip kind of deal, and then the end of time. Just kind of looking at that, kind of really, really uplifting things. The end of our universe. Okay, but it's about 10 minutes there, so you can watch these two videos, and then basically there's your homework, which is an assignment at the end here. And this homework, again, if you look, it's only 7 problems. Okay, you check out those homework problems, and we should be good to go. Remember, when you're submitting your homework, make sure that you don't just send me one page. See if you can get all the pages on there. Um, I'm being pretty lenient on that. And again, since we only have really one assignment this week, make sure if you're missing any assignments or you need time to go back on those, make sure you're getting those done. If you have any questions, as always, I'm here for you. And just remember, email, email, email. And other than that, have a great day. Team Atron out.